So this is the section 12.3 lesson video for physical science. And so as always, if you want all my videos in one place, you can subscribe to my channel and they'll all be there. Alright, so in section 2, we covered Newton's first and second laws of motion. So today we're going to talk about Newton's third law of motion and momentum. So a force cannot exist alone. Forces always exist in pairs. So for example, if I push up against my whiteboard, the reason I'm not falling through the board is because the board is also pushing back on me. That's what makes me stay and not pass through the wall. According to Newton's third law of motion, for every force there is an equal and opposite force. So if you've ever heard for a reaction, there's a reaction. That comes from Newton's third law of motion. So the force object A exerts on object B is called the action force. So in my case, my action force will be me pushing against the wall. That is me being object A, applying a force to object B, which is the wall. The force that object B exerts back on object A is called the reaction force. So the fact that the board, which is object B, is pushing back at me is the reaction force. So I apply the action force in one direction, the board applies a reaction force in the opposite direction. So action-reaction forces can produce motion, like when a swimmer takes a stroke. Okay, so if you look, your action force is in this direction, your reaction force is in this direction. So the swimmer pushes the water in a backwards direction. So as that swimmer takes, well here, let me turn this way so I can be in the same direction as the swimmer. So as the swimmer takes the stroke, the swimmer pushes the water in the backwards direction, so behind the swimmer. And then the reaction force is the water exerts a force on the swimmer, which propels the swimmer forward. So every time the swimmer pushes back against the water in a backwards direction, the water pushes the swimmer in the forward direction. That's how there's movement. There doesn't have to be movement though. For like my example, when I push up against the board, because the board is pushing back, there is no movement. Action and reaction forces do not cancel. If you remember, we talked about net forces pointing in opposite directions and they cancel. Those are forces that are applied to the same object. In an action-reaction force, they don't cancel because the two forces are applied to different objects. So like I said, I'm applying a force this way to the board. The board is applying a force in the opposite direction, but it's to me. It's not like two forces are applying themselves to the board. So another example would be like the hammer and the nail. Like when you hit the nail, the hammer is applying a force to drive the nail into the wall, but the nail is also applying a force in the opposite direction on the hammer. That's why over time you'll start seeing dents and dings in the hammer because of that force that's being applied every time it hits a nail. So remember, action-reaction forces do not cancel because they're on different objects. Normal forces in opposite directions will cancel if they're on the same object. So momentum. Momentum is the product of an object's mass and its velocity. So product, of course, in math means multiplying. So an object with a large momentum is hard to stop, and the momentum for any object at rest is 0. So because it's the product of mass times velocity, if you're at rest, you have a 0 velocity. So anything times 0 is 0, so you have 0 momentum. And then the larger the object, the heavier it is, the harder it is to stop. So for example, if somebody rolls a bowling ball towards me, I can just reach down and stop that. But if there's a car coming at me with the same velocity, I'm not going to be able to stop the car because it has a lot more momentum because it has a larger mass. So momentum is actually represented by P. A lot of people, they'll call it MOM for momentum, but it's actually represented by P. And it is mass times velocity, or M times V. So P equals M times V. So momentum is P, and it again kind of has some weird units like we talked about with force. It's a kilogram times meter per second, but it doesn't have its own special unit like newtons or anything like that. Mass, as always, needs to be in kilograms, and velocity, as we already know, is in meters per second. So when you multiply those two together, nothing cancels, so you're just left with kilograms times meters per second. So let's talk about the conservation of momentum. So there are lots of laws of conservation of blank. Whatever's at the end of it, be momentum, energy, charge, mass, matter, any of those things, it means whatever's at the end is not created or destroyed, or the total is conserved, which means it does not change. So according to the law of conservation of momentum, if no net force acts on a system, so if we have a system and we're not applying any external forces, the total momentum of the system does not change. So what that means, for example, is this is like people playing pool. When you hit one ball up against another, that other ball is going to absorb the momentum from the first ball. So the first ball will end up stopping and it will propel the other ball. So that's what we mean, as long as no external forces are acting on it. Because could we stop the yellow ball if we want to by applying force? Yes, we could. But then we have an outside force acting on it. Alright, so in a closed system, the loss of momentum of one object equals the gain of momentum in another object. So this is where Newton's cradle comes in. I know y'all have all seen it, where you take one that has the balls that are hanging, you take one and it goes doop, 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 back and forth, back and forth. And so that is one ball passing its momentum through until it hits the other ball, and then that's what propels it out. Now eventually, of course, this is sometimes referred to as perpetual motion, but eventually it is going to stop because of things like friction and air resistance and gravity and all those other forces acting on it. So that's why we say things like in a closed system. In reality, there are other forces acting on these things. So if you do have a Newton's cradle, it will eventually stop. And that's just because, like I said, it's not really a fully closed system. So let's knock out this section assessment. So using Newton's third law, explain what is meant by action and reaction forces. Okay, so remember, action force is object A applying a force to object B. Reaction force is object B applying a force back on object A. Okay, so action force is object A, which in my example was me pushing against the board, was object A applying force on object B, and my reaction force was object B applying the force back on me, object A. So state in your own words the formula for momentum. I'm not really sure what kind of question this is. I made the PowerPoint, but I don't come up with the questions. I just take them out of the book. I don't know how you state in your own words a formula. The formula for momentum is P equals m times v, or momentum equals mass times velocity. So what is a necessary condition for the conservation of momentum? Remember, there can be no net force acting on the system. Okay, no net force acting on the system. And then explain how Newton's third law of motion is at work when you walk. Well, when you walk, you apply a force downward on the floor. Like as you're walking, you are pressing down on the floor. Do you fall through the floor? Well, hopefully not, because what is the floor doing? It is doing a reaction force pressing up against your foot. So when you're walking, your action force is pushing down on the floor. The floor's reaction force is pushing up on your foot. If there was no reaction force when you push down on the floor, your foot would just keep going down. But since it doesn't, that means the floor has to be pushing back up on your foot, and that's why you don't sink down into the ground. Alright, and then last one, if an eagle and a bumblebee are traveling at 8 kilometers per hour, which has more momentum? Explain. Well, it would be the eagle, because momentum is mass times velocity. They both have the same velocity, but who has more mass, an eagle or a bumblebee? Hopefully we all answered that with the eagle would have more mass. So once you multiply the eagle's mass by 8, you would get a larger momentum for the eagle. So hopefully you have a better understanding of Newton's third law of motion and momentum.